Good evening, everybody, here in the Science Gateway Auditorium, and also for those of you online. Welcome. My name is Chris Lubkeman. I have the privilege of being the head of the Strategic Foresight Hub at ETH in Zurich in the Office of the President. And most importantly, for this evening, I have the honor and pleasure of being your guide through this evening's journey. The journey of possibility, probability, dialogue, and probably even a bit of debate. A journey where we weave the known, the unknown, the speculative, and the spectacular into a narrative of possible futures. Ladies and gentlemen, welcome to Sparks 2025, Imagining Quantum City. Great to be here. Now, as you know, CERN is no stranger to the edge of the unknown. This is a place where curiosity has been institutionalized, and the bold act of asking what if is part of the daily rhythm. It is the place where the universe's deepest secrets are casually unraveled before lunch. Today, we are bringing that spirit of a different scale of exploration, not the quantum world inside the atom, but the quantum potential of the world around us, our communities, our infrastructure, our cities. We are here to ask, what does it mean to imagine a quantum city? Each of you hopefully have come this evening with a few ideas. Can quantum help us address the profound challenges of our urban environment of the future? Will we finally be actually able to have a sustainable urban society? Critical questions. So tonight we're going to be walking between the domains of the technical reality, not technological, technical reality, speculative fiction, and a little bit of science fact, or a lot of science fact. The quantum city challenges us to reimagine the very systems that sustain our lives. It will be a place where particles and pedestrians alike can be in two places at once, just until they're measured or observed. A city built not of bricks and mortar, perhaps of probability and paradox. Tonight, Professor of Architecture Carlo Ratti will start off by laying the metaphorical foundations of the quantum city, and then I will have a wonderful conversation with three further guests. Nicolaus Giesing, professor of quantum at the University of Geneva and the Constructor University, and then a deep dive into quantum communication with Johannes Sepulveda from Airbus, and our final guest, Sabrina Maniscalco, I always mess your name up, I'm so sorry. Professor and entrepreneur will share her views on quantum computing. After this, audience, my dear audience, we will together take part in what we call the Quantum City Hall. Now, at this point, it's very important that you will be posing questions to the panel. I will be channeling your questions to them, and you need to be using this QR code with your phone. This one you're allowed to get out your phone and snap and then share your questions with us. Because during the town halls, any town hall, it's when in a democratic republic, you get to voice your opinion, get to ask your questions, to challenge the opinions. So make sure you're taking advantage of that and our four incredible humans we'll have up here. Got it? No, you can do better than that. Got it? Yeah. All right, there you go. That's good. Thank you. I appreciate that. Now, before we start our journey, there are two more little things I'd like to share, a little bit more about Sparks and then about our partners. Sparks is CERN's annual flagship conference, which brings together renowned scientists and specialists of diverse fields from around the world, embracing a multidisciplinary approach to addressing some of our biggest problems. And it's very crucial that we realize this event depends upon incredible people, incredible support to make it happen. And so therefore, we'd like to really say for this year's edition of 2025, a huge thanks to our partners and our sponsors, our donors. First and foremost, the CERN and Society Foundation, who have been supporting and promoting the mission of CERN in disseminating its benefits to the wider public for well over a decade. Also, to recognize the donors of Rolex, who has generously supported CERN's outreach activities for many years, the Hasler Foundation, the Hasler Stiftung, whose aim is to promote advancements in ICT, information and communications technology, the Foundation Althea, whose mission is to help inspire and support individuals in following their aspirations in innovation and entrepreneurship, which is fully aligned with CERN's outreach objectives. We also would like to thank the Geneva Public Transit. How many of you came with public transit tonight? Very good, very good. And those who came in the last tram we waited for, welcome. We're glad you could make it. Maybe you saw the advertisement in the trams that was advertising the event tonight and in the buses, so we're really grateful for sharing that word with the larger public. And finally, from those sponsors, and I never can get this name right, Le Temps, something like that, Le Temps, all right? Are you close enough? Okay, I can't get to helping with our visibility throughout the year. The Swiss Physical Society has also been helping us with content and promotion of the event, and is even helping co-create a card game, which you'll be able to grab some pieces from with the Periscope at the University of Geneva, which is offered to you. It's a fun way to dive into the world of quantum physics, and at the end, there'll be some of the authors of those cards will be out there giving you cards if you would like to have them. They're going to be collector's items, be able to be auctioned off. You'll be able to say, I had the first edition. In another 5, 10, 25 years, who knows, quantum, it could be. So that's it from me for the beginning. Are you ready to get started? Had enough of me so far? Yeah, that's good. Okay. Now, I am very, very pleased to welcome to the stage Ms. Charlotte Warda-Kaule. She's a Director of International Relations at CERN, up to the green circle. Charlotte, welcome.
Thank you so much, Chris, for your brilliant introduction. It's truly a privilege to welcome you all most warmly to a very unique event that will conclude this public event season at CERN in the International Year of Quantum. CERN is a place of research. It's also a place of reflection, and Sparks is a special platform for enabling a broader reflection with many other communities about the role of science in tackling the major challenges of today. To many, quantum may seem abstract, far away from the realities of everyday life, but at CERN, quantum is woven into everything that we do, from the particle collisions at the LHC to the way we detect and interpret the results. Through the Quantum Technologies Initiative, we explore and harness quantum technologies for advancing high-energy physics. With the Open Quantum Institute, we work with partners to see how quantum computing can help to advance achievement of the Sustainable Development Goals. Quantum is really part of our daily reality. Quantum at CERN also reminds us that some of the biggest mysteries are hiding at the tiniest scales. But the potential impact on our world of quantum mechanics and of quantum mechanics is truly vast. And we're thrilled to use the framework of the city to explore how quantum can impact our individual and also our collective future. With experts from quantum technology and many other fields, architecture, as part of a truly interdisciplinary dialogue. Today, we are invited, all of us, to dream about what quantum technologies may bring in the future. Naturally, there are many uncertainties on this journey. But we know, here at CERN, as has been demonstrated here, that fundamental research can really profoundly impact our daily lives, from the invention of the World Wide Web to breakthroughs in medical applications, from superconductivity to advances in computing. CERN has long been a hub of innovation, working closely with industry and other partners to explore the technologies of tomorrow. So tonight we will explore how quantum is emerging. It's often seen as one of the technologies that has the greatest potential to transform our lives in the years to come. Quantum computing, ultra-secure communication networks, next-generation sensors and materials. This frontier science may unlock possibilities that were once purely theoretical. So let's together imagine quantum city, but first a bit of theory so that you can also dive into the extraordinary and fascinating properties of the quantum world. Thank you.
Technology. It's how we measure progress, not only in what we've built, but in what's become possible. In just a century, the world has changed in ways few could have predicted. At the end of the 1800s, science fiction writers like Jules Verne imagined a future filled with machines, flying cars and moon cannons. For the most part, their world was loud and mechanical, built from materials they understood. So how did we get from steam engines and gears to algorithms and microchips? In the wake of the Second Industrial Revolution, while technology was scaling up, a few scientists were busy trying to understand the world at the smallest scale. And what they discovered changed everything. Quantum mechanics describes the world of subatomic particles, which it turns out aren't even particles, they're waves of probability. In 1925, the publications of Heisenberg, Born, Schrödinger, and others established the basis for the mathematical description of this world, launching the first quantum revolution. This massive shift led to the invention of lasers, electron microscopes, MRI machines, and the transistor that underpins all modern electronic devices. Today, we might not have flying cars, but we have computers the size of a fingernail, millions of times more powerful than the old computers that would fill entire rooms. Meanwhile, scientists combined quantum mechanics with field theory and relativity, creating quantum field theory, the foundation of modern particle physics. At CERN, fundamental research focuses on testing and expanding the quantum field theory known as the Standard Model of Particle Physics, our most precise description of the microworld to date. The original 100-year-old quantum theory promises to bring the quantum world into many more aspects of our lives. In the 1930s, Einstein, Podolsky, and Rosen pointed out a strange consequence of quantum mechanics. Particles linked in a shared state we now call quantum entanglement could influence each other instantly, even across vast distances. But according to Einstein's theory of special relativity, nothing should travel faster than light. This paradox remained a philosophical puzzle for decades. But in 1964, while working at CERN, physicist John Bell formulated the Bell inequalities, which could be used to test this daring idea experimentally. In the 1980s, groundbreaking experiments led by Alain Aspect and others confirmed that quantum entanglement is real, just as quantum theory predicted. And its applications could once again change the world. In 2020, CERN launched the Quantum Technology Initiative to explore the potential advantage that quantum technologies could bring to the high-energy physics research programs. We have now entered the second quantum revolution, one where quantum entanglement isn't just studied, it's engineered.
Thanks, CERN, for that. That's actually quite interesting for me, and I'm sure for many others in here as well. I'm not a physicist at all, so I'm still trying to get my head around quantum. Even after working with their amazing speakers, I'm still feeling I'm in a couple places at the same time, but I'm not quite sure. Our first speaker this evening is a friend of mine. His name is Carlo Ratti. He's a man of many talents. He's an architect, an engineer, author, curator, dreamer, researcher, and professor at MIT. There he leads the MIT SENSEable City Lab, which investigates and anticipates how digital technologies are changing the way people live today and their implications on the way they'll be living tomorrow at the urban scale, which is quite interesting for us, especially with the theme tonight, of Quantum City. So let us welcome to the stage Professor Carlo Ratti.
Thank you.
Welcome.
Thank you. And good evening, everybody. It's a great pleasure to be back at CERN, a place that's been very special in the past for me, for inspiration. And also this place with the name of Sergio Marchioni, with whom I worked and got to know quite well before he passed away. So I wanted to share with you today something about cities, more as an introduction to quantum cities. We're just starting to look at quantum cities, and more people after me will talk more about the potential. So SENSEable Cities is the name of our lab. It's at MIT, but also around the world, in Milano, at Polytechnic, in other places. And in order to tell you about cities, I wanted to go back to Roman times. Ancient Romans had two words for cities. One was urbs. Urbs is a physical city, made of stones or bricks, today or steel or concrete or glass. But also there's a civitas. And a civitas is all of us. It's a community of citizens living in the city. Now, the reality is that in the past, we've been able to learn about the physical city, about the urbs, very well. This is 1747, Nolli, Giambattista Nolli, the map of Rome that kind of revolutionized urban cartography. But we haven't been able to look at the civitas. But today, we're starting to do it. This, you see, this is Lisbon, for instance, mapped like a living organism, with all the flows happening there in real time. And so today we can look at not only the urbs, but the civitas at the same time. And the reason for that is actually we see a convergence. It's a convergence that's between the physical space, you see it there, and also the space of data we collect in the city. So I want to share with you how this has evolved over the past 20 years, and also how in the future, quantum can actually help us to unlock new dimensions. Let's go back to the early 2000s. That's when we started our lab at MIT. And at the time, the data you had was kind of a spatial resolution of around 10 power 2, say 100 meters, 200 meters on, and a temporal resolution of, again, something similar, 10 power 2, 10 power 3 second. Now, at the time, what you do was something like this. This was actually at the Venice Biennale. I'm the curator today, this year, of the whole Venice Biennale. At the time, we were invited for a pavilion 19 years ago, 2006. And there, for the first time ever, we actually look at the city using communication networks in real time. That was a pavilion. What we did was collect data from an Italian city, in this case in Rome. The data was shipped to MIT near real time. At MIT, in this kind of proto-cloud, we would analyze it, visualize it, and then send it back to Venice and display it in real time. Now, that was 2006 was a special year in Italy. Is the year that that summer Italy won the soccer World Cup. It was Italy and France playing. And, and we're actually looking at this with all the data from the cell phone network in Rome, and look at what happened. That was the city of Rome. You see the Colosseum, you see the river. People moving here and there through the city. And then you got the early afternoon. Still before the match, you see it there. And then in a moment, the match begins, and silence. Nobody talks anymore. And then France scores, Italy scores. Half-time, people go to the bathroom and make a call. And then second time, end of normal time, first overtime, second, the famous headbutt by Zidane, some of you might remember. And then finally, Italy wins. Now, big applause. Yeah. But you see here, and then you can see the next day how people are moving. But the key thing here is actually, at the time, it was the first time this was done. Today, it happens every day, every moment in our pockets. We say Google Maps or any type of maps. But at the time, it was the first time looking at networks in order to look at the city as the living thing. And with that, I'm putting a few papers for some of you who are interested in looking at them. They're all available on our website. But from that, we then, in the following years, we look at the interesting things with that resolution. Like, what is a city? If you want to study cities, we need to define them. And, there's not a clear definition. Well, with data and mobility data, we can do it. Or in this paper, we discovered an interesting law. I will not get too much in detail. It's just an extension of a law that was very well known 100 years ago, developed by Zip and Dudder, about how we move in cities. But actually, the new data allows us to add a new dimension, and that's frequency. So it's that regularity that was known over space. Now, with the new data, like what we were saying, can help us to expand this law on the space of frequency. But then let's move forward 10 years, and we go to the 2010s. And at that time, you got, spatial resolutions like, 10 meter, and temporal resolution is, again, 10 seconds. So you've got an order, 2 orders of magnitude difference in time. In that case, we can look at other things. In this paper, for instance, what we did, you see it in a little video. We can have a bit of sound. But that's real data in New York. Again, resolution around 10 meters. Those are taxis. Every little dot is a taxi. And here, mathematically, we ask a simple question. What is the minimum fleet of taxis to keep New York on the move? So somehow today there's a lot of inefficiencies. You see it there. You know, if you look at taxis in New York, they're vacant 50% of the time. And so we find a better way, mathematically, this is the absolute optimum to match demand and supply, then we can actually have a more efficient system for travel. So in this case, what is the minimum fleet to keep, as I was saying, New York on the move? And you see it here, like today, just by applying a bit more intelligence to the city, you could reduce, as you see, the number of taxis from 8,400 to less than 6,000. But also, if you think about the future with self-driving, you can get like something where you can run a system, a city, with 50% of what we have today. So when you got that data, that's the type of analysis you can do in the city. And again, you saw it before. This is a full paper, if you want, again, on the website. Or other things you can do. This is actually the same type of resolution with people moving. That's Boston. For those of you who know Boston, that's the Charles River. MIT is to the north. You've got Boston downtown. You see here images of Boston and San Francisco. And so with this data, we could finally solve something that puzzled me since I was a student at Cambridge. When I was a student at Cambridge, I was in this college, Cambridge, UK. That's called Darwin College. And it was something I was going from the college to the department following one route. And normally, statistically, I would go back from the department to the college following a different route. And you can imagine that would bother me a lot. You know, I was doing rational studies, but myself, I was irrational. I wasn't following the shortest path. The shortest path is, you know, between A and B is always symmetrical. So A to B equal B to A. So in this case, we realized we looked at the data from hundreds of thousands of people in Boston and San Francisco and realized actually that I'm not the only one. We all don't follow shortest path. We follow something that's called like vector-based navigation. We work with colleagues in brain and cognitive science and in other disciplines. But basically, bottom line, you see it here, is that our brain evolved probably tens of thousands of years ago when our ancestors were in the savannah and had to spare cognitive power in order to look at a possible lion and attack coming from left and right, develop an algorithm that was much easier to compute, which is actually minimizing angular deviation. It's not the shortest path, but it's somehow is good enough. You don't waste too much. But then if you do it, A to B is not the same of B to A. Or I'll give you another example when you get to this level of resolution of the analysis you can do. Here we got interested also in waste. Our cities produce a huge amount of waste. If you look at my computer up there, which is this computer, today you know everything about it. You can track every chip in it, see where it originated, how it moved on the planet, how it became that machine. Now, a few years from now, then you're going to sell this computer. At one point, you're going to give it away. And sometimes that ends up like that. A lot of waste ends up where it shouldn't. So what we decided to do, again, looking at this scale, was to develop a little tag. We had to engineer it. That's almost engineer a miniature cell phone with a difference. Your cell phone needs to send a lot of data for a short time, say 1 day. This has to send very little data for a long time, and in particular, the location of where the waste is going. It's a little bit like what you do when you go to do nuclear medicine, and they put a tracer in your blood, and they follow it through your body. The idea was, could we do the same at the scale of a city or at the scale of a country? So we did the first deployment in Seattle. We had 500 volunteers. They came with 3,000 pieces of trash. We put a little tracking tag on all of them. Anything from banana peels to e-waste. And after tagging all of them, we started following them. So here you can see the day of deployment. 3,000 objects in Seattle. After a few days, you see the main landfills next to Seattle. But I was a big surprise how far stuff started to travel. Sometimes in crazy, unpredictable ways. Look at the trace that went all the way to Chicago, changed its mind, and went back to California. and it's still moving after 1 month or 2 months. Now, we discovered this, when we did it, nobody had a clue about this because everybody was doing just a small piece of the chain, but this was the first time the whole chain was actually mapped. And it's still moving after 1 month or 2 months. Farewell Symphony seem the appropriate music for this. So this will give you a sense of what you can do then when you get to the level of resolution. And then we get to now, to the 2020s. And then you got spatial resolution is kind of 1 meter, temporal resolution is 1 hertz, the frequency is 1 hertz, 1 second. And then you can do other things. Let me give you an example. We started looking at stability of infrastructure. That's a bridge, a famous bridge actually from the 20th century that collapsed in southern Europe a few years ago. And the reason it's collapsed is that it wasn't monitored. There's other examples. This bridge didn't collapse. It's a bridge next to MIT. It's called Longfellow Bridge. I would walk on the bridge a couple times a day. The MIT campus starts to the left. That's the Charles River. But actually, that bridge, it was at one point they discovered it was about to collapse. And then it had to be rebuilt at a huge cost, a financial cost, but also a cost to the city. Connections from one side to the other, from Boston to Cambridge, were interrupted. Sorry, from Boston to Cambridge, were interrupted. Only one way you could go for a number of years. And the reason for that is that today, when you are monitoring a bridge, usually you do it either with a sensor, you see there to the left, or by sending people for inspections. And when you combine the two, the cost is significant. You can spend $500,000 per bridge per year, and we'll never be able to monitor all the bridges in the country. So our idea was, well, what you're getting, when you're doing that, you're actually looking at vibrations of the bridge. But guess what? Today you got so many things to monitor vibrations. Our cell phones, our smartphones have accelerometers, gyroscopes. You see 3 smartphones. You also see a professional accelerometer there in orange. And so we decided, what about if we could use data from this in order to monitor infrastructure? And we decided to start from this bridge. You all know this bridge. What is it? Yes, the Golden Gate. And the reason is that you got a perfect ground truth. What you collect can be tested against a lot of data that's being collected because the Golden Gate has been monitored. It is monitored in a very, very sophisticated way. So we took our car with our sensor and started going across the Golden Gate, back and forth, monitor all the data. After 100 times, the San Francisco police got a bit suspicious. But still, by the time we had collected all the data we needed, which is this, and then we analyzed it. It turns out, actually, we're doing quite a lot of research on this, that actually with the data from our smartphones, the second paper we have is using data from apps, an app like the Uber app, then you can actually get information about stability of the infrastructure. So that opens the way to being able to monitor, say, all of the infrastructure in Switzerland, or in a whole country, or in the United States, just by using data that we collect through our smartphones. And that's when you get to that resolution, those are the things you can do. There's other things you can do. This is a paper from just a few weeks ago, and we actually looked at something else. It's optic fiber in our cities, in this case in San Diego, and it turns out you can take optic fiber and repurpose it like a sensor, like a microphone distributed over a line that allows you to do the same as geophysics, what people do in geophysics, looking at waves that go there. Now, instead of geophysics, where you usually produce a wave and you see how it propagates, here you measure the wave, and what you can do is the opposite. Look at what generated it. And so you get beautiful information that you see here from just this fiber about trucks passing, about traffic, about things that happen in the city to very, very high resolution. You can even see, all the waves produced because there's a break at school, or so it becomes a way of how we can get information about, in this case, all anonymized information about the activities that goes into the city. And that's a paper just came out a few weeks ago. So I'll start to wrap up here about say what next, and open the way to the next conversation. Well, the point is that we are getting even more high res. I'll give you a few examples. In this project, this is a favelas in South America. It's actually Rocinha, the biggest favelas in Latin America. And here we started collecting data with LiDAR. With LiDAR, you collect hundreds of thousands of data and every second. So the amount of data resolution and precision is just a few millimeters. In this case, actually, this is to understand it better, to understand the stability. A problem with favelas is sometimes you got landslides. Another problem is about people don't have property titles, so the mayor committed, saying, well, if you can describe the space in a precise way, we can give property title to people, so they will be like proper citizens, not like squatters as they are today. And so I'll show you just an example. It's from another city, it's from actually Amsterdam, and still the LiDAR data, how much richness you can get. So this is actually the canal in Amsterdam. We're using this for a number of reasons, to monitor the city, but also to run self-driving boats in Amsterdam. It's a project we're doing with AMS, TU Delft, and Wageningen University. And you see here, every second you got 300,000 data points, accuracy of a few millimeters. So that's, by the way, that's how robots usually see the city. We use eyes, they see, even self-driving cars or self-driving boats usually use the LiDARs or something like this. And the interesting thing is that, little by little, the whole city emerges. And also you can collect data over time, you can look at the stability of quay walls. It's a big problem in Amsterdam. So you get this kind of very accurate description of the city, much beyond what we saw at the beginning. Remember a beautiful map of Rome by Nolli. And we're just starting looking at also quantum. This is not our paper. The others were a paper from our lab, but this is not. But it's a paper we find very inspiring. It's a paper from a couple of years ago that actually starts to look at getting gravimeter to such a resolution that we couldn't have a few years or a few decades ago, that then you can look at this kind of underground cartography for city. Also very important for applications, but also for better understanding the invisible in our cities. So I'll finish here this as a segue to the next part. So I want to tell you that I'm sure many of you have seen it. If you haven't, you should watch this beautiful movie. It's called Power of 10 by Charles and Ray Eames. The looks at the universe and connecting from the human scale. You start from the human scale and zooming out, and on the other side, zooming in all the way to atom and subatom. So this kind of zooming is what's happening in our cities. And so really there's a very interesting new phase when resolution goes even to the next step, where quantum technology can help us to understand new dimensions of our cities. Thank you.
Come here, and thank you, Carlo.
Thank you, Chris.
Thank you. I took a couple of notes. I want to ask you a couple of questions here.
Sure.
Come into the late. So
Sure.
Here we go.
Yes.
So I liked very much the built and the lived.
Yes.
The built and the lived, and you spent a bit of time.
The urbs and the civitas, like the old Romans.
yeah, exactly.
Or you could also use another analogy. It could be also the hardware and the software. But I think the Latin one is better, the physical city and the community.
Okay, the physical city. So when you talked a little bit about quantum sensors, what could you imagine that quantum sensors could do for us to be understanding either one of those, especially, I say, the community better?
Yeah, and I think, what we saw before in a little introduction is also how we can reveal the invisible. And some of the things we've seen before is also this. And I'm pretty sure there's a lot of invisible dimension, both of the physical city and the community, that we could actually understand better. And the other interesting thing about this, I think, this is what I find very special here is kind of the collaboration, a large-scale collaboration. When looking at the scale, and I think we need much more of that also, at the scale of the city. That's the point we're making at the Venice Biennale. If any of you is in Venice, do come visit us until November. And that's the point. About these issues we need to tackle in a similar way to how we tackle other problems that the problem tackled here at CERN.
So what is the boundary with collecting the data? Because here at CERN, they have like thousands of data points every microsecond, whatever, But for you, with your work, can you imagine what would be your dream scenario to collecting data?
Look, I think data means knowledge. Data means we know the cities better. We also need to pay a lot of attention to data. I'm very concerned about data for two reasons today. One is that a lot of data ends up in places, especially our data. I'm not too concerned about data in cities in Europe, but I'm concerned a lot of data collected in our pockets from our phones. That data ends up in servers. We don't know what it's used for. Mm-hmm. So I think we need much more transparency in the way we use it. And I also think another thing that bothers me is I didn't show it tonight. We're using a lot of deep learning. This kind of black box system. You train them, and they do a number of things. Now you train them with data. They're nothing if you don't train them, like an empty brain. But if you train them, they can do amazing things, like LLMs. But when you're doing that, today we're training that, and we're not opening the training set. I think that's very important. If you could have an adversary training set, and you might discover it when it's too late. So anyway, the data is knowledge, but I think data should be shared much more and used in a way that's much closer to open source, and again, to a lot of the things happening here.
So it's open science, right?
And more. Yes.
All right, Carlo, thank you. Thank you so
Chris.
very much. It's a pleasure.
Thanks a lot, Chris.
Here we go. Thank you so much. So now I would like to introduce our next guest, Nicolas Guizin. Sorry if I messed up your name as well, sir. He is a Swiss physicist. He's a local, which I've learned today, which is quite wonderful. Professor at the University of Geneva and the Constructor University, delivered world-leading work in the fields of experimental quantum cryptography and long-distance quantum communication over standard telecom optical cables or optical fibers. He also founded one of the very, very, very early quantum groups, IDQ, and is a company which provides quantum-based technologies and probably found in some of your phones potentially here right now. If not, we kind of wish it could be. We're going to talk about that in just a second. So, Nicolas, please join me on the stage.
Hi, Chris.
It's a pleasure. So you're a native boy.
Yeah, I was born here. Well, not here, but
Not here.
in Geneva.
In Geneva. Yes.
Yeah,
I think you're probably one of the very few I've ever met who's actually from Geneva. It's a
Yeah, well,
pleasure.
my mother was from Germany, my father from Basel, so I'm a typical Geneva guy.
I love it. Well, let's sit down and have a talk about your quantum journey. So, Nicolas, what does everybody in the room need to know about you and quantum?
Well, I'm a quantum fanatic, maybe. You know, when I was a student, I was, during holidays, obviously, reading papers. And
Wait. You were reading papers on your holidays?
Of course. I'm a physicist.
Okay. Yeah.
Every scientist does that.
Okay, every
You need
student does
holidays
that,
to
right?
have time.
Okay, all right.
So you take holidays, you take papers, and very quickly I got absolutely convinced that I will have a quantum life, or I will dedicate my life to quantum. So I became a quantum physicist, studied all that. But then the next question, should I become a theorist or an experimentalist? You know, most physicists, they divide like that. And I thought, that's nonsense. Why should I do only half the job somehow? Moreover, what kind of project would I like to do? And I thought, well, it has to be either intellectually fascinating, that's maybe on the theory side, or it has to be potentially useful. That's more the experimental and industry side. Mm-hmm. So I decided I do both, and I'm still doing both.
That's wonderful. So back up just a second. What caught your eye or your heart or your head with quantum? What was it that caught you?
You know, at some point, I realized that we, with just our brute mental force, are able to dive into this quantum world of atoms and photons. And although this world is really completely different, being at several places at the same time, as you said, and so on, but you start understanding that just by indeed some kind of brute mental force. It requires quite some time and effort. It's not trivial. No one is going to understand that in 5 minutes. Impossible. You know, journalists often ask me, can I explain quantum in 5 minutes? The answer is very clear. No, I cannot. Impossible. It took me decades, you know.
Yeah.
So it's impossible. But anyway, the fact that we are able with this, with our brains, to dive into a world which is that different from our world is totally fascinating.
Yeah. So you studied physics, you decided you wanted to join these. Tell me about the beginning of your journey, because we talked about optic fibers.
Yeah, so the fact is, okay, after my PhD, so PhD was in theoretical physics, but then, okay, wife, a child, it's complicated, so I decided, okay, at some point I need also to make some money. So to work. And so I joined a startup, but at that time that was still in the 80s, so pre-internet. I joined a startup to work on classical optical communication, so optical fibers and things like that. That of course contributed to the internet revolution. And somehow I did in this startup a second unofficial PhD, but more on the experimental and industry side. And then I had a chance to go back to the university, leading a group on classical optical communication. And the first thing I did is to buy a single photon detector. because a single photon is the smallest grain of light. It's the smallest you have. That's one of the findings of Einstein. And so being able to detect this very, very teeny quanta of energy, of electromagnetic energy, is just fascinating. So I bought it. I had no idea what to do with it. I played with it until I read a paper again, and the paper was about the idea of quantum cryptography. So I understood the idea, and I realized I know optical fibers, I have a single photon detector, I understand the theory, and so we were the first doing quantum cryptography. At that time, I have to say, the detector was not suited for standard telecom fiber. So we used first special optical fiber, but very quickly then we developed the technology to detect also photons, so this grain of light, at the wavelength that correspond to telecom optical fiber. And then we did quantum cryptography under Lake Geneva. Now, it's a good title for a paper, and that changed my life and started a revolution.
I love the title of that paper, Quantum
Cryptography under Lake Geneva.
It sounds like a romance or something. It's a romance for a physicist. So what happened with this? Because quantum cryptography has become quite a domain, and we're going to hear a little bit more about that in a little bit. Sure. So tell me, what happened with that? What did you do?
Oh, well, so then we 23 years ago, so we established a company, you mentioned it, IDQ, ID Quantique, in Geneva, or in Carouge. And so we really started commercializing this. So you have really fibers that go hundreds of kilometers, or maybe Geneva, Lausanne, to mention two cities. And you can really distribute a quantum key. But now I say a quantum cryptography key. That's the application. But let's go back to what we saw before. Einstein, Podolsky, Rosen. The quantum correlation that Einstein, Podolsky, Rosen were found so mysterious or spooky, to take the wording of Einstein, is actually exactly the same as a cryptographic key. Somehow, this action at a distance, as again Einstein was saying, with nothing mediating it, if there is nothing that mediates it, there's obviously nothing to spy on. And nevertheless, you get the two ends getting the same randomness. That is exactly a cryptographic key. Or maybe for the people here, I should just say a password. A password should be random, and of course has to be the same on both sides. So we distribute, with this company, we developed engines, systems that, let's say, distribute automatically passwords. Well, it could be a very long password, so you can use it, or your computers can use it to communicate in absolute security, confidentiality.
And so this became the firm you founded, and and that was a device that was...
Yeah, okay. So, of course, the first one. So there's also maybe two things. There's quantum cryptography, which is really distributing over long distances. And indeed, the first one was, okay, now
I remember my father had a cell phone. It was like a brick,
Yeah. But then you have the other thing, Chris. You have also that for whatever cryptography, quantum or classical, you need randomness. You need to have a source of entropy, as we say. Okay. And indeed, at the end of the last century, I was very proud because with some students in my lab, we made a quantum random number generator about that size. This quantum, maybe I should just say a little bit. So you take a photon, you let it, maybe with a beam splitter, go to several places at once, delocalized, and when you detect it, and boom, sometimes it ends here, sometimes and where it ends, or where it gets detected or observed, is random. So that's the basic idea. But then you have to turn it into something, that you could sell. And so my first realization was something that a small shoebox. And I was very proud. So small, wow. And then we founded this IDQ, and their engineers, they made it matchbox, centimeter size. Wow. And during years, we sold that one. But then we, engineers are amazing people. And then...
I appreciate that. I'm an engineer.
You're an engineer.
Yeah, thank you.
Yeah, but
I knew I liked you for a reason. So now I know why. Yeah.
And then, so these guys, these engineers, they made this quantum random number generator millimeter size, super, super small. And this super small, so it's like a chip, everybody here has probably seen a chip. Not the chip that you eat, the electronic chip. And these ones are found today in some of the Samsung smartphones.
Okay.
Unfortunately, the apps are so far written only in Korean, so not very useful to us, or at least to me. But nevertheless, there are millions of these phones, and they are used in South Korea to communicate with banks, with hospitals, and I don't know.
So you've taken the shoebox, and now you've put it into the phones.
Wait, Chris, I have to show you that.
Oh, really?
Because I happen to have one.
No.
So you see?
Seriously?
Yeah, you have actually two of them here. Do you see it? Yeah, you see it. Yeah.
Are they up there too?
So the small one here,
yeah.
Exactly. So the smallest one here, actually, so it's very small. It's really millimeter, maybe 1.5 or 2 millimeter size. And why don't you have it?
Okay, thank you. So I am the now proud owner of a quantum device.
Exactly. These are two quantum devices.
Ooh.
And so
Without any tariffs, I appreciate that very much. This is a very...
What do you have here in? You have a source of photons, then photons expand, and then you have an array of detectors, and of course one of them will detect the photon, and that's really producing the randomness. And each of these chips produces something like 1 million random bits per second.
I'm impressed by that. I'm not quite sure exactly why I'm impressed, but it's a big number and it's pretty cool. So I like that. I can't relate it to anything. So, but we're here to talk about the quantum city, and this is for me very cool. It makes it very real. It's already around. There are individuals who have quantum devices.
In Seoul, yes.
Yeah, in Seoul, not here. And you saw Carlo talking about some ideas about the quantum city. What does the quantum city bring to your mind and your heart?
Maybe let me say two things. The first is again about cryptography. So in cities you have cars, or maybe in the future some kind of transportation engines. And in a car, already today, when you want to open the window, you press a button, but there is no longer a direct connection. There's actually communication. In the car, everything communicates with everything, and there you need cryptography, because you don't want to press the button in your car and it's the window of the next car that actually goes down.
No,
would be really
maybe depends who's sitting in the car.
Yeah, okay. If it's just the window, that's okay, but the same could happen with your driving wheel.
Sure.
You see, so you need that.
Interesting.
And this kind of quantum solutions is certainly part of the future cryptographic solutions that we will all be using.
Interesting.
Probably even obviously without even noticing it. Maybe something else. Carlo was talking about quantum gravitometers. This is something extremely real. It exists. There are companies. There is one that I could mention now in France. But there are several groups working on it. And even now with atomic clocks so precise that if you lift it from here to here, because of relativity, general relativity, it would run at a different speed. And the latest result, if you lift these atomic clocks by just a millimeter, you would already notice it. So these clocks are not useful to keep time, because we don't need to keep time with such an accuracy. But for instance, to measure gravity, to measure, you could have a GPS with sub-meter resolution, maybe a millimeter kind of resolution. And then you need, you need also all the software and the infrastructure to be able to use all that. But for the gravimeter, that's a pretty straightforward application.
Interesting. I mean, I'm quite fascinated by how you're saying that it's here now. It's the quantum components of the quantum city are here now. Yeah. And yet there's still a lot of air, a lot of space, a lot of wires, a lot of entanglement ahead.
Yeah, indeed. So things like the random number generator in your hand, already exist, but there is still room for enormous improvement. Quantum computers were also mentioned. These ones are still baby quantum computers, the existing ones. And here we need enormous development. Also for quantum cryptography, I told you 100 kilometers or a few hundreds of kilometers, so you can cover Switzerland. But if you want to make it really global, you need to go to thousands of kilometers, and that is still a lot of development. That, okay, Geneva University, Constructor University are working on it, and many, many, many more.
Fantastic.
And also industries, large industries also working on that.
That's fantastic. Well, Nicola, it's been truly a pleasure to speak with you. I feel like I could talk to you for hours, but we don't have hours. Unfortunately, we have 10 seconds left. So with that, I want to say thank you very, very much for joining us on stage, and we'll see you back on stage in a little bit.
Thank you.
Merci beaucoup. Thank you for this. Very cool. Now, I just want to like to reiterate, you can ask questions of us up on stage, of Nicola and our other guests who are going to be coming, of Carlo, so make sure you're looking at the QR code and typing them down. We're now going to watch our second CERN capsule. We've had 3 of those in total, so our second one's going to be coming now, which explores how precise timing, down to the billionth of a second, powers not only our daily lives, but also the frontiers of science and quantum communication. Ladies and gentlemen, I'd like to present to you the White Rabbit collaboration. So let's go down that rabbit hole together.
Timing is at the heart of the modern world. From morning alarms to train schedules, from global markets to digital communications, synchronization is everywhere. Sometimes down to a billionth of a second. At CERN's Large Hadron Collider, protons collide every 25 billionths of a second in perfect sync across a 27-kilometer accelerator ring. In 2011, the White Rabbit technology was developed at CERN to provide means of precisely synchronizing such systems across tens of kilometers. This is where the World Wide Web was first proposed in 1990, shaping the internet as we know it today. As we move towards a future quantum internet, this new CERN technology could again prove to be key. Today, computers and other digital devices exchange information encoded into long chains of zeros and ones. This information travels through optical fibers as series of light flashes, where a light impulse is 1 and a gap is 0. For a typical 1 gigabit link, 1 billion flashes and gaps have to be transmitted every second. The transition to quantum communications is going to pose a whole new set of challenges. Rather than using pulses of light, quantum technologies employ pairs of single photons produced in the fragile state of quantum entanglement. The first challenge is to maintain this state while the photons are being transported to the sender and the receiver. The second challenge is synchronization. For quantum communication to work, the sender and the receiver must know which photons are entangled with each other. To achieve this, they must have their clocks synchronized very precisely. The photons are not labeled in any way. The only way to identify them is to measure the time at which they arrive. If the sender's or receiver's clock is late by even a tiny amount, the photons will get mixed up, and quantum communication will simply not work. And if there are billions of photons per second, the clocks of the sender and the receiver need to be aligned to a nanosecond, 1 billionth of a second. So how to achieve such precise synchronization over large distances? Enter White Rabbit, the technology created to ensure that the White Rabbit is never late again. White Rabbit can ensure that 2 clocks tick together with an accuracy of a fraction of a nanosecond. The technology uses standard optical fiber links with dedicated White Rabbit network switches. It is being used in telecommunications, financial networks, and research applications like accelerators, detectors, or radio telescopes, and also in an increasing number of quantum projects. A system connecting 2 cities with a quantum link using existing fibers, the development of a network infrastructure connecting multiple quantum computers into a single distributed system. Transmitting quantum entangled photons and white rabbit network traffic simultaneously in the same fiber. These are just a few examples of white rabbit applications in quantum communications. The technology is available under the CERN Open Hardware License. In 2024, the White Rabbit collaboration was established. It is open to companies and laboratories looking to work together and receive support in using and further developing the technology to set the pace for an ever faster moving world.
I can't help think of the Matrix and the little white rabbit for those who know the Matrix. Yeah, I heard that. Thank you. Thank you. I appreciate that. Yeah, well, okay. So, our next guest is Johanna Sepulveda. She is a senior expert in quantum secure technologies and technical domain manager for quantum technologies at Airbus Defence and Space. At the policy level, she's deeply involved with European quantum initiatives such as the European Quantum Communication, European Quantum Infrastructure, and the Strategic Advisory Board of the Quantum Technologies for the European Commission, and the Strategic Industry Roadmap of the European Quantum Industry. I'm not sure if I like the acronyms better. You know, I think I might just go with those next time. It's good. She is a person who is truly working hard to ensure that quantum is on the European science roadmap. Let us welcome Johanna to the stage.
Good evening. It is a pleasure to be here and discuss the role of quantum communication in the cities of the future. So let's start and help me by inserting in an exercise. Let's imagine a city where everything is connected. Your car, your fridge, your hospital records, even the voting system. The city itself breathes digital. It seems smart, it seems efficient, but also it might be vulnerable. One day you woke up and everything went dark. The critical infrastructures are shutting down. The emergency systems do not respond. All the traffic lights are suddenly hacked. So suddenly this smart environment becomes very dangerous. So this is, and it really looks like a dystopian film, and it will be a chaos. So for this environment, security must, and it is a relevant piece for this environment. So let's go out from this scary movie, and let's discuss today the quantum communication in the future cities. At Airbus, we also design secure communication, not only the great airplanes, but also secure communication for cities and also governments. These secure communications are against the threats of current and future computers and attackers. So I'm Johanna Sepulveda, and it's my pleasure to share here at CERN my view regarding these technologies. The main message that I want to let today is that quantum communication is not science fiction. It is here, and it is essential if we want to have the cities of tomorrow. And let's start by the guilty one. Yes, you see here the quantum computer. So quantum computers, these kind of machines that are very attractive because they have this potential of overcome the performance of the current computers. The performance for certain applications, and it includes complex systems, it includes also optimization problems, even enhancing AI capabilities. But what is not really talk about is the security risk that this quantum computer poses. So quantum computers will be able to solve the hard mathematical problems on which current security is based on. They represent a serious threat to all applications. So let's understand the problem. So data is the nervous system of modern applications, and it will be even more relevant in the cities of the future, where the high connectivity is essential. Today, most of our secure communication using banking, emails, critical infrastructures relies on shared secrets called secret keys. So you can think on it like digital padlocks. It only works if sender and receiver knows the correct key. That is the right combination to unlock it. And here is the challenge. These secrets need to be shared between devices. Usually, they have to cross networks that can be intercepted or hacked. In order to protect this key exchange process, we use hard mathematical problems that act as a secure digital envelopes around this secret key. Currently, these envelopes work very well. However, powerful quantum computers will be able to break these mathematical envelopes, thus exposing the secret keys. And if someone stole the key, they can unlock everything. They can know your secret communication. But then you can tell me, Johanna, these kind of big quantum computers and powerful quantum computers are not yet here. So why do we care now? Yeah? So let me explain why. So we have different applications. They have different life cycles. It is expected that a powerful quantum computer will arrive at any moment during the next 10 years. So once these quantum computers arrive, they will put at stake all the communication. So that means that we will need to start a transition process towards quantum securing systems. And as I said, it is a process. So that means that it will take several years. And in fact, this is not the first crypto migration that we have to face. We know that it will take a long time and a lot of resources. During all this transition, all security communications will be exposed to attacks. And in addition, an attacker can record your secure communication today, store it, and decrypt it in the future with a quantum computer. So that is why we need to embrace the quantum secure solutions now. So what we can do? There are two main alternatives for implementing quantum secure communication. The first one, new secure cryptography or post-quantum cryptography. They are algorithms, new and different algorithms that rely on hard mathematical problems that are resistant to attacks performed by classical computers and by quantum computers. So yes, we still have hard mathematical computers that can resist these quantum computers. The second alternative are the quantum communication or quantum cryptography that is based on physics and that requires the integration of a new quantum infrastructure. These two security technologies are very different. How different? It is like the difference between using a stronger envelope to make the key exchange and to use an envelope that will disappear if you try to pick it. It is expected that these two technologies are coexisting in a quantum secure city. They are not really competing. They will fulfill the requirements of the different applications. So let's start by the post-quantum cryptography. So if we think in post-quantum cryptography, you might assume that it is easy to migrate, that the secure systems, all the secure systems and using this technology anyway, it is just an algorithm that might be executing in different devices. What might go wrong? Everything can go wrong. So let me tell you. So first of all, we have a wide variety of post-quantum families, 5 families. In each of these families, we have, or we can identify different algorithms that are characterized by a wide variety of characteristics in terms of performance and in terms of security properties. So the first challenge is that to all our applications, we have to map these kind of algorithms that are able to fit the requirements in terms of performance and security. And in addition, we will not be able, and we shall not, just drop to the trash all our systems. We will need to update them. Nevertheless, not all the system will be able to handle the new algorithms in an efficient way. So new chips, new hardware, new software should be developed, and we have to update our secure systems. And the final concern, and which is very relevant, it is that these algorithms, they rely on mathematics, and they will stay secure until we discover a new algorithm able to break these new hard mathematical problems. How likely this is? This is difficult to quantify. So there are some applications that cannot take this risk. And for that, we have the quantum cryptography or quantum communication. We have seen that for exchanging secure communication, we need to share a key, and also if we want to, for example, exchange our medical records, we can ensure that we can communicate, and we want to communicate in a private way, we can use this kind, or now we are using this kind of method, but also we learned that with quantum computers that will not be possible. So how to exchange this key? So let's use physics. So quantum communication, what it's going to use is particles of light called photons and their quantum properties in order to send secret keys through quantum channels. And this is what is called quantum key distribution. And what is the advantage of this kind of mechanism? So we know that the quantum information cannot be copied, and in addition, any eavesdrop or interception will be detected. So it's not just hard to hack, it is impossible, unless you break the laws of physics. And this, it is some characteristics that are very relevant for different applications. So quantum communication is already being deployed through terrestrial and space segments, allowing to reach a wide and cover a wide field of the Earth. So future cities aren't just about thinking on the smart buildings and smart sensors. They are about resilience. They are about secure environments. So think about autonomous vehicles, think about AI-driven healthcare, AI applications. Think about voting systems. So all these applications demand long-term security. That means that data must remain untampered, and the communication must stay private, and systems must keep trusted. So quantum communication delivers a truly future-proof security. To the architects here in this room, you are designing the physical layers of tomorrow's cities. This new infrastructure must be taken into account into your landscape. To the policymakers, you are shaping our digital laws. The use of this technology also must be taken into account. So this is not longer a society, this is not longer a physicist concern. It is still, but it is also an engineering problem, it is a design challenge, it is a political and policy question, but it is also a societal decision. And here is the exciting part. This is not just research, it is happening today. So demonstration of such networks date back of 2002. And today, they are widely deployed around the world, from individual components to complex devices, up to truly fully operational terrestrial and space system networks. These systems are already serving customers, delivering quantum keys for secure communication, as seen in China and South Korea. In the future, these quantum networks will not only use for the key exchange, but also for transmitting quantum data between quantum computers and quantum sensors, and all this infrastructure will be called the quantum internet. At Airbus, we design quantum secure networks. We are also developing the space segment for quantum communication, enabling quantum secure links for satellites to cities below. I was the chief engineer of the EuroQCI, the European Quantum Communication Infrastructure. The initiative was signed by all the EU member states already in 2019 to build a pan-European quantum network to protect Europe's critical infrastructure. During all this time, I'm very excited in witnessing the wide deployment of quantum networks across all EU member states. So they are ready, they're deployed now, different demonstrations. So Europe is firmly committed to build this secure infrastructure to safeguard its citizens. This technology is real. It's being built today. So we reach the end of this presentation, but not of this journey of the quantum communication. And now we are in a crossroads. One path leads to a smarter, faster cities built on aging, fragile digital foundation, or we can think on quantum secure communication and lead to cities that are not just smart, but secure by design. Cities where communication is safeguarded not by hope, but by quantum secure communication. Quantum communication is here, it's working, and we must take it seriously. Thank you so much.
Thank you. Thank you very much, Johanna. It's really fantastic. So I have a couple questions for you, if I may. I wrote for your notes here. Hacking versus secure comms. So this is something you started off with this idea of unhackable, because the quantum security, secure quantum solutions. So, and you're saying these are here now. Right? We have this already. We heard from Nicola that he also has some of this. I mean, so we can already anticipate this to now? I mean, can I go buy it?
So these services, currently what I told in China, South Korea, we have the first users, so they are really buying these services. However, in order that it is deployed and used in a secure way, we need certification, we need the study and exploration of the security on the implementation, because we know that the theory it is perfect and it is very secure. However, many of the attacks are derived from the implementation of these technologies. And this happens also in the classical technologies. So we must take care about the imperfections on the implementation and make sure that the implementation is as close as possible as in the theory.
That's really cool. Well, thank you so much again for sharing your wisdom with us. And we're going to see you back up here in just a minute.
Thank you so much.
All right. Thank you. So we're all going to stand up here in just a few minutes, but not quite yet. We're going to have our third CERN capsule, a short little video. This is now dedicated to the CERN's involvement in quantum computing. So we've heard a little bit about quantum computing so far. Now, with the Open Quantum Initiative, we're going to hear a little bit more about it. So enjoy.
When big data is more important than ever, one place is playing a key role in understanding it: CERN. Here, the pursuit of knowledge meets the front lines of innovation, from the smallest particles to the grandest systems. And now, a new frontier is emerging: quantum computing. At CERN, experiments generate massive volumes of data, terabytes, petabytes. Every second brings opportunity for discovery. To harness it, CERN pioneered grid computing, adopted early AI techniques and cloud computing, and now explores the transformative power of quantum technologies. In 2020, CERN launched the Quantum Technology Initiative to explore the potential advantage that quantum technologies could bring to the high-energy physics research programs. And CERN computing activities, including quantum and AI, don't just serve science, they serve society. That's where the Open Quantum Institute, OQI, comes in. Hosted by CERN, born at Jezda, supported by UBS, OQI brings together quantum scientists, sustainability experts, industry, and diplomacy. Its mission? To ensure quantum computing benefits everyone. And it starts by tackling some of humanity's greatest challenges like clean water. Water is essential. Yet in many cities, half of it is lost to leaks, old infrastructure, or illegal use. Day zero already struck Cape Town and Sao Paulo, cities with no water left. What if we could effectively detect leaks where they happen? Classical computers struggle with the complexity of urban water systems. How can quantum computing help? With OQI, researchers could model vast water networks and optimize where to place detectors, saving resources and improving lives. This is just one example of quantum for the Sustainable Development Goals. From zero hunger to clean energy, healthcare to climate action, quantum computing holds promise in a number of different domains. Through OQI, CERN is opening doors for global cooperation, real-world application, and inclusive innovation. Because science should not only advance knowledge, it should empower humanity. The quantum revolution is here, and with it, a new way to imagine and shape our future.
All right. Before I bring our next guest up to the stage, I think she deserves our unabashed attention. So I'd like everyone to stand up just a minute. We've been sitting for a little bit more than an hour. Just stand up for a minute, shake a little bit. Otherwise, I don't know, she's got so much to share with you. You want to be awake, all right? So here we go. We're going to try to be in two states at the same time. Present and physical, intellectual and emotional. I don't know, you can pick your two. And as we surf the quantum wave. Is anybody having fun yet? Yes. Have you learned something new? Yes. Yeah? All right. So thank you. We're going to sit back down and I'm going to bring our next guest up. She really truly does deserve our 100% attention. At least I didn't make you do the hokey pokey or anything like that, right? You've all been to away days where you have to do these games. No, we're not going to do that. Here we go. So, our final guest this evening before our panel is Sabrina Maniscalco. She is a professor of quantum information, computing, and logic at the University of Helsinki. She is the CEO and co-founder of a very interesting startup called Algorithmic. It's focused on quantum algorithms for life sciences. She has coordinated several international interdisciplinary projects and is recognized as one of the world's leading experts in quantum tech. Now, she's in Finland, but she's actually Sicilian. So how better of a human to represent quantum than this? So Sabrina, welcome to the stage. It's great to have you here. Let's give her a good hand.
Thank you. Wow. That was the most amazing introduction ever. Good evening, everyone. It's a pleasure, really, and an honor to be here at CERN. This is a place renowned for making the invisible visible and driving, of course, scientific revolution. He already pronounced my name correctly. Chris, thank you so much. Sabrina Maniscalco. What we do at Algorithmic is really pioneering programming quantum computers. So we are developing software and algorithms to simulate molecules and materials, and we do this combining quantum and HPC. So the question of today for you is, how can quantum computers transform the cities of the future? Can we use the power of quantum computers to make them healthier, more sustainable, and truly inclusive? we'll try to go through all of these questions. But first of all, if you think about cities, we typically envision a skyscraper, we think about streets full of people, we think about traffic, and really busy roads. But underneath all these visible elements, there is a hidden molecular reality. Every breath we take, every glass of water we drink, the batteries that power electric vehicles, the material that forms all these buildings, all depend fundamentally on molecules and how they interact. And to build and maintain sustainable and thriving city, we really have to understand very deeply this hidden molecular universe. And quantum computers are very powerful and exactly able or enabling to do so. So cities magnify both opportunities and challenges. Consider, for example, air pollution. Air pollution is responsible for many respiratory illnesses, for chronic conditions, and it affects really at large urban population. Consider antibiotic resistance infections that are increasingly emerging from crowded urban environments. Consider, for example, cities and their needs for sustainable energy solutions, for cleaner battery, and for smarter transportation systems. Now, environmental friendly infrastructure is what we really need. And solving this challenge requires really to change profoundly, to really go through scientific breakthrough that are really deeply going at the molecular level. This is precisely the promise of quantum simulations, and this is where quantum simulations run on quantum computers can really help. So, why, however, can't conventional computational system handle this molecular problem? And the reason really is related to complexity, the complexity of simulating molecules using classical computers. And this complexity is really related to the exponential number of variables that are needed to really model single molecules, even simple molecules, in an exact manner. So imagine if you think of predicting how molecules interact biologically, then it becomes clearly impossible even with the largest supercomputer. So classical computers approach these tasks really in a way by brute force. And this results in this exponential complexity. And in a way, it's like mapping an entire rainforest using pencil and paper. Now, quantum computers, on the other hand, they are fundamentally different. They are naturally quantum mechanical objects. And it's like learning from nature how to simulate nature, because they encode naturally quantum information that allows to simulate molecular interactions accurately and efficiently. So it's, in a way, it's learning to speak the language of nature itself. Quantum simulations, therefore, can revolutionize urban life in profound ways in the future. So imagine, for example, dramatically accelerating drug discovery, rapidly identifying effective treatments for diseases that are really caused by urban pollution. Think about batteries that are specifically designed at the molecular level, really to store renewable energy efficiently. Imagine of powering sustainable electric transportation in densely populated cities. And envision constructing buildings from materials that are both safer and environmentally benign, preventing harmful chemicals from polluting urban ecosystem. So all these really allows to imagine a future where we can simulate even chemical pollutants in urban waterways and design precise cleanup strategies. Quantum simulations have the potential to turn these visionary possibilities into concrete realities. Now, where are we now? At Algorithmic, we are already applying quantum simulations in real-world collaborations with pharmaceutical and biotech industries. We are starting to design the use cases that are already combining quantum and supercomputer and AI in order to enhance the design of molecule. And this experience really shows us the immense potential to translate the same quantum computing and simulation method into urban-focused applications. So we are can be optimizing molecular level processes in wastewater treatments. It could be advancing green material science for urban constructions, or enhancing battery chemistry for citywide electrical vehicle networks. So quantum computing is set to become the ultimate scientific companion to urban innovation. This is what we want to see. You might wonder, how close are we now, today, to achieve this quantum-enabled breakthrough? We have baby computers, but we also have adolescent, teenager computers, because when coupled with supercomputers, right now, we can use hybrid quantum classical approaches that allow really to already now use emerging capabilities by, in some way, mitigating errors. Something very similar to when you use your headset, the noise-canceling headsets. And this is what we have started to show. We have shown that with current technologies, we can already simulate molecules that are in phase 2 clinical trials, of course, combining them with classical simulations. And this allows really to bring practical quantum computers much closer, and therefore to reach quantum advantage, the demonstration of really in commercial and scientific ways, superiority of quantum computers with respect to classical, much, much closer, to see that this will happen very soon. Now, for a moment, let's really travel forward in time. Let's go to year 2050 and imagine what a quantum city might look like. It's a city where healthcare is precisely tailored at the molecular level for the individual needs. This makes personalized medicine accessible to every human being. It's a city built with sustainable materials optimized through quantum simulations. This results in buildings that are not just carbon neutral, but carbon negative. It's a city powered by renewable energy, with quantum design catalysts that can enable clean, abundant, and efficient energy storage. The quantum city, this quantum city, isn't just a vision, but should be a realistic roadmap for our future. And this can happen if we fully embrace quantum innovation. In closing, I want to emphasize a fundamental truth, or something it's not a fundamental truth, it's something I deeply believe, may not be a fundamental truth, but to transform cities sustainably and responsibly, we must first master the invisible molecular world beneath them. Quantum simulations really offer us the potential to really have this transformative breakthrough of making invisible processes visible, complex problems solvable, and distant futures achievable. And together, we can indeed build quantum cities, healthier, greener, and inclusive urban spaces, starting today, one molecule at a time. Thank you.
Thank you. I think I've decided I'm going to nominate you to be the quantum advocate of the century.
Thank you.
That was incredible, because I could imagine living in the city you've just described, the place you've just described, and I just wrote a few notes. The language of nature itself. Tell me more about that.
Yeah, of course, this is perhaps the most fascinating aspect, I think, of quantum physics. And of quantum simulation itself. Quantum simulation was the way in which quantum computing was firstly envisioned by Richard Feynman. And it's particularly exciting because there is nothing more fascinating than discovering and understanding the fundamental laws of nature. And come on, we are at CERN, so obviously this is clearly really one of the mission of everyone who works here. But at the same time, we can use this learning to engineer new technologies. This is the shift that has happened recently with the second quantum technology revolution. Understanding nature, simulating nature, in order to build new technologies for humankind.
So thank you. So tell us a little bit more about the work with your company? I mean, because you're looking at life sciences, drug discovery, or what is actually you're doing there?
Yes, I mean, of course, life sciences, drug discovery, these are really very extremely complex problems, clearly. So what we are doing is that we are helping our clients and end user to identify those problems in, for example, a drug discovery pipeline, which can be actually tackled by a quantum computer, which this is absolutely non-trivial. If you think in terms of chemistry, actually perhaps 80% of chemistry can be treated classically very well with approximate methods, okay? But there are some problems which are really, really hard, where all the power of supercomputers and chemists really struggle. And in this case, we have example of collaborations, for example, with Cleveland Clinic in the US, where we identified certain molecules used for an alternative therapy for cancer treatment, photodynamic therapy, where actually they came to us with a problem of simulability classically, and we identified actually this is exactly the type of problems where quantum computers can help. So we are building the pipeline. We already have demonstrations on real hardware. For now, for 40 qubits, 54 qubits already run, and we are aiming at 100 qubits. Qubits are the fundamental units of quantum information, and these will lead very close to really quantum advantage. Already with devices that move towards, becoming more and more perfect, fault tolerant, we call them.
I'm sitting here trying to imagine, because I'm old enough to remember the days when computers just had a green screen that had text that came across.
Yes.
I'm trying to imagine how we're going to be interacting with the quantum world, the quantum computer, the quantum learning from nature.
How in practice you do it? Well, I mean, I would say that one of the main lessons to learn is that quantum computers are devices that, of course, work according to quantum physics. So the algorithms and methodology, the way in which you have to program them is absolutely completely different from the classical devices. You have to use a different way of thinking, and the type of problems that are really solvable on quantum computers, the way in which you extract information is really different. So it's fascinating because it can be very counterintuitive. At the same time, it's a great challenge, and it's beautiful, again, because you keep learning. It combines fundamental physics with applied physics, with chemistry, with life sciences. I find it, I'm obviously
I think you like this. Yeah, I think you're into it. Yeah, that's really it's beautiful. Thank you so very much for sharing this with us, really your passion.
Thank you.
Let me come out here. So, we had the pleasure of taking a tour this morning, and I want to thank CERN for that, to see a little bit behind the scenes, incredible work of the physicists and the engineers together. And my big takeaway was, I need to take a physics class. My last one was almost 40 years ago, and I think things have changed since then. Now, we have a bit of a surprise for you, and not even our speakers know what it is. While waiting, I'm going to remind you to post the questions. I have a little device over here where I've been seeing them. Got quite a few very good ones coming in. There's still room for more. Please share those with me so that afterwards we can be talking about those up on the panel. And I will do my very, very, very best to answer all of them, but I can't promise that I will. But we shall give us a very good try. Now, I believe, gentlemen, I'd like to introduce two musicians who have joined me up here on stage, Marc Therese and Pablo de Mena Fantao. They're going to be singing a song entitled Quantum City. So a round of applause for Marc and Pablo.
City when particles dance on the future spreading. Oh, won't you please take me home? Take me down to the quantum city where particles dance on the future spreading. Oh, won't you please tell me why? Calling the proposition. I'm a web function with some ambition. I'm your and thank you for your professional mission. I'll meet the Ratti and don't play. Quantum further either way. Hey! Qubits, or so they say. You gotta keep this thing up all mixing alive. You know it's old, it's starting to try. You treat it like a mystery crime. Everybody dances in time. Come on, hey! Take me down to the quantum city where particles dance on the future spreading. Oh, won't you please take me home? Take me down to the quantum city where particles dance on the future spreading. In the water's matter culture leads us to something larger. A future where the city's clean and bright. Ideas growing through the night. Tell me, don't I feel just right? Take me down to the quantum city where the particles dance on a I'm ready. Oh, won't you please take me home? Take me down to the quantum city where the particles dance on the future's running. Down to the quantum city where particles dance on the future spreading. Oh, won't you please take me down? Take me down to the quantum city where particles dance on the future spreading. Oh, won't you please take me home? Take me down to the quantum city where particles dance on the future spreading. Oh, won't you please take me home?
Gentlemen, fantastic. Thank you so much. And I think, does anybody recognize the song, the tune? Yeah. Who was it? Guns N' Roses, maybe? Yeah, that was it. There we go. Quite fun. So thank you both, gentlemen, very, very much for your rendition of Quantum City. Now, we're heading into the final part of our program tonight, and I would like to invite all of our speakers to come up on stage, please. Come on up. This is where you, come on up. Come on up, where are we? Gonna save the time. Where are they? Come on. Carlo, where are you? Carlo Ratti, there you are. Come on in. Okay. Now, I have quite a few excellent questions here, and I'm going to start off with one. Now, panel, you can phone a friend. you can, I'm just kidding. So, here's a question that's come up, and it's quite a good one. It's got the highest rating of all. How can Switzerland and Europe remain competitive in this domain? So, who wants to take that? Go for it. Easy question. Go ahead, Nicholas, and then Johanna, I'm going to ask you to...
Yeah, so this is a very good question. CERN, you know, the E stands for Europe. And actually, all the basic fundamental research on quantum was carried out in Europe. You know, all the old guys we saw in the introduction video, it's always all happened in Europe. Today, the US is leading this development on the industrial side. And I believe, indeed, Europe, including Switzerland, has here something to change and to improve. Not that nothing is happening. Quite a lot is also happening in Europe and in Switzerland. But I think we should really ask our governments to make the conditions better so that the wealthy people and companies can share some of their wealth with those creating the future.
Easy solution. We can, okay, check, we'll work on that one. No, so Johanna, you're at the European Union and you're like up there. What's your view on this?
So when we talk about quantum, we're talking about the three different pillars: quantum computing, quantum communication, quantum sensing. For each pillar, we have champions. When we think about quantum computer, the champion is USA. But I think quantum communication, I think the one that is leading is China. But quantum sensing, Europe is leading.
All right, here we go. Good.
Exactly. So we have several assets. I think one way, and the European Commission is investing in further developing capabilities, not only in the fundamental research, but now in the newest strategy that Europe will put on the table, is to bring these kind of technologies from the lab to fab. And for doing that, we know that it's a very complex system. We need to work together. We need to foster demonstrations, see the capabilities of these technologies in the field, in the different applications, and start to drive and optimize and guide these technologies into our society.
Okay.
Maybe if I, maybe to add a small thing, I think if Europe is able to rise to the moment, I think there's very interesting opportunities. I see more and more colleagues who, for different reasons, want to come back to Europe or go to Europe. So I think, I think there's an interesting opportunity, and I think it's up to us, all of us, to try to, rise to the moment and make sure the politicians also do that. So I wouldn't be so pessimistic.
There we go. Okay, we're going to stay with that. So here's a good question. Here's, what are the challenges we need to overcome to create the quantum internet? All right, who's going to go for that one? All right, it's a good question. The first internet was created here, so we want to do the second one. What do we need to do?
I think that we need to further develop some components, and one component and piece that is missing is the quantum memories. So currently, in this quantum secure communication, we are using in a relay mode, in which at each node that we are relaying, we have to transform from the quantum information, and we have to transform into classical and store into classical memories. Okay. And this put somehow some threats in security, so that's why these nodes have to be under some security measures. But we also somehow lose some throughput. So in order that we can link quantum computers, link quantum sensing, we still need these quantum memories to develop.
Okay. I see, Nicholas, I see you shaking your head. You're nodding, as you said.
No. So I fully agree. That's absolutely correct. We need quantum memories. Why do we need them? If you send photons too far away, even with the best optical fiber, they get lost at some point. So you cannot, depending on the rate, you have some limits. Let's say 100 kilometers, something like that. And then you need to connect them here. So you have one pair here, another pair, and you need to connect them in the middle. But to connect them, they have to be there at the same time. And that's where you need memories to synchronize your network. And maybe one more thing, if you allow me, because that's so fascinating. What do you do here then in the middle? Actually, you teleport these photons to here. We didn't even mention the word quantum teleportation. Yeah. But it's really, you really teleport these qubits, this elementary quantum information, to here. It's amazing that you can do that. And indeed, today you have even, the Chinese actually demonstrated quantum teleportation over 1,000 kilometers via satellite. Amazing. And this is really part, so you see that's again where my fascination for the theory combines with the application and potential useful quantum network of the future.
So the Star Trek transporter is going to be real within my lifetime.
Depends how long you live.
A good answer. I like that one. So after quantum communications and crypto, quantum computing, quantum sensors, what do you believe as a panel will be the next big breakthrough?
The next
big breakthrough. What big domain? So we have.
You mean in still in quantum or more generally in other domains?
I'm reading it verbatim. I can give you my interpretation, but it's sort of like. But I think it's an interesting question. We talked about quantum comms as one domain. Let's say in cryptography, you'll be able to. So it has secure communication. Quantum computing. We talked a little bit about the potential for that with the algorithms and being able to solve massive amounts of data. In quantum sensors, is there something else? Or what do you see could be the potential next blue, white, green, purple space for quantum to get into?
Maybe I'll take a stab at it, but from a different point of view. I think there's so much intelligence in nature that we still need to uncover. And think about, if you look, we're all excited about ChatGPT. This system is just something where you load it with some information, it can regurgitate it in a way that makes more or less sense, which is going to be very interesting. It's going to have a big application, but a huge cost. Think about the beauty of the human brain and how much it can do with so little power. So I think, if I need to look at this in a broader sense about where today we got a lot of excitement about technology and, again, AI, intelligence, I think the next revolution will be unlocking some of the incredible knowledge that is in nature, in biology.
Okay, great.
Maybe if I can add something. If you think about what quantum computing is combined with the machine learning and combined with AI and combined with supercomputing is effectively the next exponential technology. So let me make an analogy with GPUs. Nowadays, we all use GPUs. GPUs initially were invented for graphic cards for gaming, right? But then users started to use them and to invent or create or think about different uses, in particular AI. So it was the community that once we had the hardware, imagined new ways of extracting, or not information, of extracting, potential applications to something that then became really what powers the current AI revolution. So my idea is that there are a lot of potential breakthrough and new innovations that will, we have not yet thought about them, because the technology is becoming mature, but as becomes more mature and as the community of users expands, as industry becomes adopting even more, as universities and research institutions and all different types of stakeholders start to really play with increasingly powerful devices, there will be a number of unexpected yet applications that, because they are unexpected, well, I cannot tell you what they are, obviously, as it has happened in the past.
So here's one thing that came in is here, could quantum simulation become a new form of policy making, where decisions are stress tested in quantum environments before implementation? We're in Geneva, after all, so someone has to ask this question around, policy making and testing world simulation. I don't know, Bucky Fuller did the world game. Maybe this could be
Of course, it's crucial. It's very important to.
I don't know. It's sort of it's an interesting
in
thought.
a way, involve already now in the discussion and in the dialogue about quantum technologies, about democratizing quantum technologies, all stakeholders, politicians, policymakers. It's something that, again, we heard here in the film, the Open Quantum Institute, and many initiatives that start from CERN. And of course, JESDA is an example in which really there is an attempt to, first of all, communicate in the right manner, really, to non-experts, because in this case, policymakers are not quantum physicists, obviously, and you have to, in a way, provide, not all of them,
yeah,
maybe
there's one or two, you know.
Some of them, perhaps. So you have to find the proper way of creating a dialogue which involves really specialists and non-specialists, and make sure that powerful technologies like quantum are used in a way that is eventually accessible to everyone and not to just few very powerful countries.
And I think currently, correct what you said, it is focused on the putting this technology to the public, because one thing that will promote the further development of this technology are the killer applications. That means what it really, we see a huge advantage. Regarding regulation, as the technology is still very young, so currently it is advised not to put over-regulation on this and to foster more the development, the exploration.
Maybe
you wanted to ask, go ahead.
Yeah, maybe I'm not sure if I understood it correctly, but what I understood was more about, well, if you use quantum and do incredible simulations, can we then change policy making? Can we then, change the way we run society? And I would say, I don't think so. And the reason is something that I don't believe in simulations, because simulations usually are the beauty of reality is all the feedback loops. And the unpredicted feedback loops that are, the difference between democracy and other systems is how everybody can react, and then you got this kind of non-linear system that you cannot simulate. So all the people who try to do simulations in order, to plan it, to have a planned economy, it was tried many times in the 20th century, it's still being tried today in parts of the world, and you see spectacular failure. So I don't know if I interpreted the question correctly, but that's what I would say. I hope we don't try to simulate. I think we need to live the beauty of interacting with each other in feedback loops, which is like how natural evolution happens, through feedback loops, trying things and see how they go.
But this is a very important point, because of course we are not, and when we think in terms of quantum simulation, we don't think about simulating human behavior, obviously. So it's important to notice how quantum computers, in general, are not universal machines that are solving any problems or any computational problems. There are certain applications and use cases where quantum computers can provide actually an advantage, and others that cannot. So, I mean, I am not aware of any applications where we can simulate human behavior with a quantum computer. So it's good. It's interesting to see a perspective that is from a non-expert. Yeah.
So here's a really interesting question I'd like to ask you all, because I'm curious as well. How fragile is quantum tech? I mean, you gave me a little chip, a quantum on a chip. So how fragile is it possible to control and easy to destroy?
So maybe here I can start being the oldest one on stage for the following reason. When I was a student, first of all, I never, during my entire studies, heard the word entanglement. And when I was asking professors after reading some papers during my holidays, the answer was, oh, you don't need to know about entanglement. It's so fragile, it's like a dream. I mean, as soon as you think about it, it's gone. And today, we master entanglement and keep it for a really long time. And long time is not maybe a day, but we can clearly keep it for minutes, or maybe the longest, I don't know exactly, but it's going to many minutes. So it's already, and during a minute, the light goes way out of the solar system, or maybe not, but beyond the sun, certainly beyond the sun. So it really goes a long, long way. And so this is a complete change. We the physicists, we thought that entanglement is super fragile, and today we know we can actually, master it and keep it alive for really, really long times. The quantum memories that you just mentioned, I think the longest quantum memory has reached an hour, if I remember well. But it's really nothing that, the world of entanglement has totally changed during my lifetime. Totally.
So, Serena, you were about to answer, and it looks like you were going to as well.
I could just say that to add, of course, to what Nicolas said, of course, quantum information is still fragile. Of course, it's true that entanglement can be maintained for a long time, and this technology improves continuously, but it also depends, I add the layer of complexity, on where quantum information is encoded. I mean, in which physical system quantum information is really encoded. So there are, for example, quantum computers that are based on really something called superconducting qubits. And there are quantum computers based on atoms or ions. There are quantum computers based on photons. And each of them have different degree of resistance to noise and to imperfections that come, from many sources of errors. And so therefore, in general, the information that, or the time of life of a quantum computer can change depending on the type of quantum computer and the time of life of a quantum computer. The duration, for which you can run a quantum computer is still terribly affected by noise, and therefore makes quantum information fragile. It's still the problem number one for quantum computers, okay? We don't have yet very resilient to noise quantum devices, but they're becoming increasingly performant, and we have also developed software that allows to make them more performant.
Well, exactly. I find it very interesting that we have some different point of view, and I think it's because first of all we are addressing different pillars, computing, communication, and also because the term fragile is very subjective. I think for some applications, you don't need a long-term entanglement. And we see that, for example, in many sensors, in medical applications, what we have today, it is good enough for doing a change and for using it in real applications. Of course, it is good to further evolve in this technology, but we already have many applications that are good enough.
So I think this is a good enough, excuse me, it's good enough, but I also think my phone, I drop it, and I've got a laptop, I try not to drop it. It's sort of semi-fragile, and you say a minute is sort of a good period of time. I'm thinking to myself, I'm not sure about that, how fragile. But it's a different definition, perhaps, of the word, what fragile is. And that's an interesting thing for me. So here's a fascinating question. We haven't talked about this. When I think about the future of the city, one of the things that always intrigued me by the work of Carlo was when he was starting to look at the heartbeat of the city. We showed this with that, the miracle wind. Right? The heartbeat of the city. And you talk about nature. And it's also quite interesting, and the question here is around consciousness, being able to model consciousness. We're trying to get closer to nature. Do we believe that could quantum computing help us and bring us closer to understanding and modeling consciousness? That's a very big aspirational question here, folks. Right. What do you think?
Short answer is no.
Oh, okay.
I think we should really be careful. Some people indeed are talking about quantum medicine, quantum consciousness, all that. No, today our understanding of quantum physics doesn't allow us to say anything about consciousness. Sorry.
Yeah, I would agree. I also know that there are people who are studying or working in the direction of understanding consciousness. Even serious scientists are working on this field. I don't see any, let's say, evidence at this stage.
That's okay. I was just curious by the question. Opinion. So it's really far from the city, but
can I again take a kind of contrarian view? So I think we will actually understand consciousness, but no, maybe not. Quantum computing doesn't need to be the key technology. It's for doing that, but I think certainly there's a lot of super exciting things that are happening now in studying the brain, and that are opening the way to perhaps understanding better consciousness. But yes, I don't see any relationship with quantum at the moment, so I wouldn't entangle the two. To use the right.
Well done. Yeah. Very good. So here's a question here, which I think is actually quite good, is for each of you to share, what do you think the future is going to look like when we see the picture of the city here? If I think back to you, gave the example of Rome, we've got many cities. We live in cities, some of us who have the streets which are laid down by the Greeks, the Romans, the Mycenaeans. These are very ancient places. Colombia has ancient civilizations. What's the future going to look like? How different will it be? How same will it be?
Maybe then I'll, playing more the architect. And I was thinking about this when looking at this picture. You're right. We still live in cities that were built hundreds of years ago, thousands of years ago. If you are in Rome, if you are in Split, in many other cities built by Romans, where we still inhabit those things. And if you think about this, what we need as humans, we need horizontal floors. We need facades to protect us from the outside. We need windows because we like to look outside and get some light. And those things. So I don't want to disappoint, but I don't think we're going to see a lot of Blade Runner cities. But what is happening in that city? Basically not the herbs, but the civitas, the people living there. I think that will change a lot. And think about how much our lives change over the past 5 or 6 years since COVID, in the way we work, the way we meet, the way we mate, the way we order food, and so on. So I think that is going to change much faster than actually the physical city, the hardware. Also, another thing, because I don't think we need to build many more cities. There's still I still talk to mayors sometimes in Europe, in Italy, in Switzerland, around the world, saying we need to do big expansion plans. And then, the question is for whom? Population is not growing, and the amount of square meters per person are not changing. So I don't think we need to build many more cities, but I think, the way we have our cities, we adapting to change, to climate change in particular, in the way we live in the cities, that is what's going to change. So I think, this image is nice, but I don't think we are going to see anything like this anytime soon.
I actually would like the others on the panel to take a stab at answering that question too.
Well, I will talk very much in general, because from the quantum computing perspective, I somehow summarize some of the possible applications where there can be an impact directly on cities. But remember that we are talking about a change between, it's really not an incremental change, between possible and impossible. What quantum computers are promising is to solve problems which are unsolvable in any other way. So if you think in terms of really how strongly computational problems are, everywhere in our life and in our society, and imagine to break boundaries of what can be actually computed. And obviously not for everything, but it can be for simulating materials, it can be for simulating drugs, it can be for, so transforming something like computational pipeline in drug discoveries into something very similar to sciences like physics and chemistry. This is a tremendous change. It's a change that is impacting profoundly the way we live, how long we live, and it will be everywhere. So that is, for me...
Pervasive. It's going to be the pervasive computing, it's going to be pervasive computing, penetrating everything everywhere.
Yeah.
Johanna,
for me, I think...
The city. Let's focus on the city and how we think of that. The picture, how do you picture it?
Exactly. So I think we have different alternatives. I really see the hyperconnectivity, but maybe the future cities will not be even in Earth. We can see in other planets. And for also living in other planets, we need better sensors, we need a different support for simulating, for computing, and we always will need secure communication. Because without secure communication, we are not going to have this connectivity. And it is because it's for nature to try to keep our privacy and to enable these kind of functionalities. So I see that quantum will be a tool to enable the humankind to a wide variety of possibilities. Yeah?
All right. Anything to add, or we can go to the next one?
No, I think I just agree with what has just been said.
Okay. So here's a couple of very short ones. Do you think that could quantum have prevented the power outage in the Iberian Peninsula?
Probably not. I don't know. Maybe. What do you think?
I don't know. It's a curious question, actually, but I thought we would just kind of throw that.
It's hard to answer. For me, it's hard to answer yes or not. I would say more no than yes, but then I would need to.
Yeah.
Well, in that case, because it was a lot about the network and the balances and so on, so maybe a better, more power, more computing power, and especially maybe to model this kind of distributed system and in production and consumption, or maybe it could have helped to have a more resilient system.
So here's sort of a slightly intriguing one. Do you believe the quantum computers will help AI reach the point of singularity?
Look, I mean, there are.
I'm asking because these are kind of getting to the end of the evening questions. We're getting ready for.
Of course, it's a very meaningful question because, of course, there is a field as part of quantum technology is quantum machine learning that is studying how quantum computers can actually empower AI and machine learning, and how these can obviously accelerate the progress and therefore reach really the singularity.
So yes.
So this field.
We're just going to summarize that. Yes, it's going to do it.
No, I don't know. The truth is that we don't know. I mean, science and research will tell. We don't know yet.
Okay.
It could be possible. I'm sorry to be like not a yes or no, but it is.
You're being very quantum here. You're kind of riding the wave in between.
It's not a yes or no question.
That's okay.
It is possible, and we will see.
Nicola, and then we're going to ask a final question for the panel before.
Yeah. Okay, so first of all, I'm not afraid of AI. Scientists are using kind of AI to do computations for decades. Softwares that allow us to do even symbolic computations. Nowadays, it's no longer symbolic computations, it's language. So it's not math, it's language. And that, of course, affects way more people. And it's very impressive what ChatGPT and others are able to do. But I don't think we should be afraid of them. We have to be afraid of not knowing personally how to use it. So everybody should spend time to learn that. On the other side now, quantum is certainly going to help AI just by providing more data. With a quantum computer, you can simulate the molecules, as we heard. And then once you have quantum simulated many of these molecules, you can feed also AI with this additional data, and that will certainly improve these AIs, yes.
Okay. I'd like you to give me one word. One word that for you represents the quantum city. When you think of the quantum city, give me the word that comes to mind. Carlo.
Well, maybe
one word.
Okay, but I need to explain why. You need to.
One word, and then you can explain.
Okay, entanglement. And the reason is because the city is about entanglement. Tonight is about entanglement. So in quantum is about the same.
Okay, entanglement. Thank you.
Well, no cheating. I had exactly the same word in mind.
Oh,
locality, you will have it everywhere.
Okay, you guys are a pair, so it's okay. I will go for that.
We're spoiling his game. What about you?
I cannot say that it's the same, otherwise.
No, you can't use it. We've already entangled. They're entangled.
I will
You're
go
not.
For the communication, so it will be secure.
Secure. Quantum city. That's great. Secure. One word.
I cannot say it because the first
thing you have to use one word.
No, the first thing I thought was ice cream. It's absolutely nothing to do. But okay, that's
no, it's delightful. Ice cream is beautiful. Gelato.
Yeah, gelato. I thought maybe because I'm hungry. I don't know. But
I love it.
It just
that's
the first
perfect.
word.
No, it's perfect.
But you said the first word.
That's perfect. I love that because gelato has many different flavors. It takes a craft. It's an art.
And Chris, and your word?
Excitement.
Ah, nice.
Excitement. It really excites me. It's been interesting to learn with you, all of you, and to do this evening. You know, you have many, many really great questions in here, and I'm ranging from the AI question, should quantum be taught in schools? Yes, of course it should be. The fragility, flying cars, we're going to get there. Security, what about the resources it's going to cost the planet? And so they're really good questions, and I did not avoid them. We couldn't answer everything. But you know, these are things which we'll be engaging over the next years. And I think it's really, it's an incredible possibility and opportunity for us to be here. So imagining the quantum city, we've all been here, we're doing it with this incredible panel, so I want to thank you for that. And I thank you for being here to do this with us as I've learned an awful lot. I'd like to give a big thank you to Dante and his CERN production team for inviting us to share the stage this evening and making it all happen so seamlessly. You guys are doing a great crew. It's a really great crew. And also a big thank you to the scientists and the leadership of CERN for your unwavering dedication to bringing new knowledge of the fundamental questions to life. This is something which you have inspired me, inspired many generations to do. A huge thank you to our donors for standing solidly behind science, the importance of science, science communication, and science in society. We need this more than ever in a very positive way, a very rational way, and it's very important for us, for all of us in this room as we go forward with this. It's also a wonderful big thank you to you for choosing to be here tonight. It is truly grateful for your presence, a full auditorium. You know you can be many different places, and to come out to hear 2 hours of science is awesome. So I'd like for you to give yourself a hand for being here. And constant improvement is a very important part of the culture here at CERN, and please help make Sparks be the best it can be. You'll be getting a survey to fill out. Please give feedback. It's really quite important. This is the final event of the season. We invite you to stay tuned for next season, which will start in October. But before this, don't miss the event in July 19th, Stellar, a voyage across the universe with astronauts and Nobel Prize winners, which will be quite exciting. You see it on the screen right there. And final thanks to our panel. Again, you have been amazing. Thank you for the journey with us tonight. So awesome. And so all that remains for me is to say good night, drink lots of water, eat an apple, walk a lot, stay healthy, and get home safely. Thank you.
Thank you.